this video, we'll demonstrate how we can use the standard normal distribution in order to solve problems involving any normal distribution with any mean and any standard deviation. Here's the problem we'll solve. Suppose we have a hospital and the birth weights of the infants born at this hospital follow a normal distribution. The mean of this normal distribution is 3,700 grams and the standard deviation is 350 grams. We'll work out the answers to these questions. What percent of infants born at the hospital weigh less than 3,000 grams? What percent of infants weigh between 4,000 and 4,500 grams? And what birth weight is the first quartile, the value such that 25% of the babies are less than or equal to that weight? Let's define a random variable x. X will be the birth weight of a randomly chosen baby. In statistical notation, we can write that x has a normal distribution with mean 3,700 grams and standard deviation 350. The normal distribution is our model for the birth weights of babies at this hospital. So we calculate probabilities as areas under this normal density curve. The peak is at our mean of 3,700. One standard deviation is 350 grams. So either side of 3,700, the range from 3,350 grams to 4,050 grams, covers about 68% of the birth weights of the babies born at this hospital. So we'd expect about 68% of the babies born at the hospital to have their birth weight in that range. Let's go to our first question. What percent of infants born at the hospital weigh less than 3,000 grams? So our small babies. We could also word this as, what is the probability that a randomly chosen infant from this hospital will weigh less than 3,000 grams? It's the same calculation. So we need this area under our normal density curve, corresponding to the probability that x is less than 3,000. Of course, if we have a computer we can get normal probabilities for any normal distribution. But if we need to rely on values from the standard normal distribution, we just have to recall that any normal random variable can be transformed to a standard normal random variable by subtracting its mean and dividing the result by its standard deviation. That is, for any random variable x with some normal distribution with some mean mu and some standard deviation sigma, z, which we get by taking x and subtracting its mean, dividing the result by its standard deviation, has a standard normal distribution, a normal distribution with a mean of 0 and a standard deviation of 1. The probability that x is less than 3,000 corresponds to this area under a standard normal distribution density function. On this standard normal density, we've shaded the area to the left of -2. And to confirm that that's the right value, giving us the corresponding probability that we want for our birth weights, the probability that x is less than 3,000 is the same as the probability that z, a standard normal random variable, is less than 3,000 minus the mean, 3,700, and that divided by 350. And that works out to be the probability that z is less than -2. And we can then find that it happens to be 0.0228. I used a computer to get that value, but of course you could also use a normal table or some other way of calculating standard normal probabilities. So only about 2% of babies at this hospital weigh less than 3,000 grams. Let's go now to our second question. What percent of infants weigh between 4,000 and 4,500 grams? To answer this question, we need this area under the normal density curve. Typically, we calculate normal probabilities as the area below a value. So to calculate this area between two values, we need to find the area under the density curve below 4,500 grams and then subtract the area below 4,000 grams. And to convert these to values from a standard normal distribution, this corresponds to the probability that a standard normal random variable z is less than or equal to 2.29 minus the probability that Z is less than 0.86. And again, we can get those probabilities. In this case, it works out to 0.9890 minus 0.8051. So this works out to be 0.1839 when we do the subtraction. So approximately 18% of babies have birth weights in this range from 4,000 to 4,500 grams. And finally, our third question. What birth weight is the first quartile? The first quartile is the value such that the probability of being less than it is 0.25, 1/4. For a standard normal distribution, this is halfway between negative 0.67 and negative 0.68. We'll approximate it as the value halfway between, that is negative 0.675. Of course, if you have a computer, you can get that more accurately. Now that's for a standard normal distribution. But we need the corresponding value for our normal distribution for birth weights, which has a mean of 3,700 and a standard deviation of 350. We've seen already that we can convert a value from a normal distribution to a standard normal distribution by subtracting the mean and dividing by the standard deviation. Now we want to go in the opposite direction, so we do the opposite calculation. That is, suppose we have a random variable x that has a normal distribution with some mean mu and some standard deviation sigma, and we have a random variable z that, as usual, has our standard normal distribution, a normal distribution with mean 0 and standard deviation 1. Then, if we take our standard normal random variable z and multiply it by the standard deviation, sigma, and add the mean, mu, the result has a normal distribution with mean mu and standard deviation sigma. So applying that to this birth weight problem, we know for the standard normal distribution that the first quartile is about negative 0.675. Converting that to our normal distribution for birth weights, we multiply it by 350, the standard deviation, and add the mean, 3,700, and we get 3,463.75. So the first quartile of birth weights at this hospital is about 3,464 grams. This problem represents typical questions that one can solve with normal probability distributions. And if you've followed the calculations that we've done here, you can solve many of these problems.